Okay. I think now we're good. So I'd like today to close this subject and close also the practical application associated with it, taking the last step towards the setup of a regional prediction model. We work on Monday on the dimensionless flow duration curve, this lowercase q you see here. We will focus today on the prediction of the mean annual flow for engaged sites. So predicting the long-term average stream flows for catchments where we do not have any observation of discharge. We will address this problem by setting up a multi-regression model in the form of a power law, something like this one, but for the study area we are working on. Okay, we have to address a few theoretical concepts to go there that deal with the setup of a multiple regression log linear model, but I usually go through it already in an operational way. We will directly work on the application. First of all, because I think that you had the past experiences of linear regression in other courses. It's a very general tool. And second of all, because I don't want to go into the mathematical detail of it. We will keep it at a, let's say, shallow level, but what I'm explaining during class, I want to be crystal clear. So in case what I'm saying it's not clear, please stop me and ask questions, okay, as usual. So our problem now is to predict the mean annual flow. There is a discharge. We want to predict it without having discharge of observation. And we will set up a power law, a model that more or less looks like this, a statistical coefficient that we need to identify based on data collected in other catchments, times a physical descriptor, let's say x1, to the power of a statistical exponent C1 times another physical descriptor. This could be the catchment area. This could be mean annual precipitation, for example, raised to another exponent that has to be statistically identified. And then let's consider the model to have P explanatory variable, P physical descriptors of the catchment raised to the power of Cp. How do we do this? This is done, normally a power law model is used because the link between discharge and physical descriptor is nonlinear or highly nonlinear. But a power law like this can be easily linearized, right? If we take the log on the left and right of the equal sign, we get something like this. Natural log of the mean annual flow is equal to, then for the properties of log transformation, is equal to the natural log of C0 plus C1 times the natural log of x1 plus Cp times the natural log of xp. Okay? This is now a linear model. So the variable we want to estimate is or actually the log transformation of the variable we want to estimate is a linear function. This is a constant, this is a coefficient, constant, this is the log transformation of a descriptor, and so on and so forth. So it's a linear function of P catchment descriptors. Is this sufficiently clear? How do we handle the identification of the best model to make the prediction? So we will use a classical tool in statistical regionalization, which is linear regression. It is a general tool. It can be useful for a variety of applications. We see its application in hydrology. Okay, so associating a discharge to, for example, catchment area, mean annual precipitation, so morphological and climate descriptors of the catchments. Correct? So it is, as you see, a very simple but also a very powerful method to identify regional dependencies, regional relationships between variables. In linear regression, we indicate what we want to predict as the predicted variable. Then we have some model coefficients, and then the predictor, in case we use just one predictor. Okay, but as you will see, one predictor is never enough to get a satisfactory representation of the mean annual flow. You want me to close? It is very hot, of course. I hope they will make a lot of noise. Let's see one more. And let's see how it goes. Okay. So this for the case in which we have just one predictor plus model error, because this is a model. It's a simplified representation of reality, so we expect to have some differences between what we predict and the empirical values. Okay. So what are the main assumptions? That the observations based on which we identify this model are independent between each other, and this is more or less an hypothesis that applies also to our case. What are the observations? Empirical values of mean annual flow and the corresponding values of the physical descriptors, right? The relationship between x and y is linear, and we found a way to linearize the dependence through log transformation. And the error is normally distributed with zero mean and constant variance. So the model is unbiased, the residuals, the errors on average are zero, and they do not depend on the magnitude of the quantity we want to predict. They have the same standard deviation for small values of the mean annual flow and high values of the mean annual flow. There's a way to statistically test this hypothesis, but we will not go into this level of detail in the course, okay? So the fact that is epsilon here is almost stochastic. It's set, and it comes from a Gaussian distribution with zero mean and a constant standard deviation. We will not go to this level of detail. So then we have some mathematical expression to estimate the coefficients of the model. So B, in case we have just one descriptor, or several values of B, as in this case, if we have more than one descriptors. If we have just one descriptor, we can estimate B and alpha based on the information we have on y and x applying these relationships. These relationships can be mathematically derived using the least square procedure. So a procedure that minimizes the summation of the square residuals between empirical values and predicted values. What do we see here? The standard deviation of the observed values of the predicted variable, the standard deviation of the observed value of the predictant, and the correlation, linear correlation between the two. Okay, and at the same time, we can also evaluate an estimate of A That minimizes the squared residuals for the model, which depends on the average value of y, the average value of x, and what we just predicted. A good indicator of the model performance when we just have one variable is the square linear correlation coefficient. You know what a Pearson or a linear correlation coefficient is. It's a measure that tells us how linearly correlated two quantities are. If it's 1 or minus 1, it means that the correlation, linear correlation, is perfect, okay? Plus 1 for a positive correlation, minus 1 for a perfect negative correlation, meaning if x goes up, y goes down in a perfect linear way. All, let's say, smaller degrees of linear correlation are associated with smaller values of rho in absolute terms. If you square rho, you get 1 only in the cases of perfect correlation, or values between 1 and 0 in case the degree of linear correlation is smaller. But I think you know these things already, okay? Is that so or not? You've never seen the correlation coefficient. Normally what you will get through a linear regression model would be something like this. Please note that values are in natural scale, but the scale itself is log. So this is a log scale, okay? Area in square kilometers is the predictor, and the predicted variable or predictant is the mean annual flow, also in log scale, okay? These are the empirical values. The line here is the model, the linear model between the two. It has an intercept, A, and a slope, B, that are identified by minimizing the summation of the square residuals between the model and the line. Okay? So far, so good. Now, in our case, we have a problem. Because as I told you, the size of the catchment normally is not enough to get a good prediction of the mean annual flow. That depends on other characteristics too. The slope of the catchment, the amount of water the catchment receives every year on average, okay? So we need more predictors to set up a good model. And the problem becomes, okay, I'll tell you what the problem becomes in a minute. With more predictors, we will have still the possibility to identify the coefficients of the model A, B1, as in the slide, or C1, which is the same on the blackboard, through the minimization of the summation of the square residuals between model and observation, okay? But using the linear correlation coefficient squared is not anymore a good indicator of the performance of the model, because now you have several x's and just one y, one predictant and several predictors. So you use normally other measures of the performance of the model. We will refer to the adjusted R-square, also refer to Nash-Sutcliffe efficiency adjusted in other, let's say, textbooks or tools. In R, you will see written adjusted R-square. What is that? It's a measure of model performance. It varies between minus infinite if the model sucks and 1 if the model is perfect. We will never see 1 because our models will not be perfect, okay? But we have to tend to 1. A good model will have high adjusted R-square values. Values around 0.8, 0.9, okay? 1, it's impossible. So let's not even keep our expectation high. It also considers the degrees of freedom of the problem in assessing the performance of the model. So it takes into account how many degrees of freedom we have. The higher the number of degrees of freedom, the better, because it means that we have a lot of data relative to the number of coefficients we want to predict. C0, C1, Cp. So the this adjusted measure takes into account the degrees of freedom of the problem, which are at the denominator here. N is the number of observations. In our application, it means the number of catchments based on which we set up the regional model, okay? If we have 11 catchments, N will be 11, because it's the number of pairs Y, X1, X2, X3. P is what? The number of predictors in the model. And if you notice, P plus 1 is the number of statistical coefficients of the model I have to estimate. Because if I have P predictors, it means that I have 1, 2, 3, 4, 5, P plus 1 coefficients to predict. Okay? So the number of observation minus P plus 1 is how many extra catchments I have to set up the statistical model. If the degree of freedom is 0, it's not a statistical optimization anymore. It's a linear system with one solution, 1, 0, that has no practical utility, because it works perfectly for your catchment, but then you apply it to an external catchment to make your prediction, and you get random numbers out of it. Is this sufficiently clear? So you want to have high number of degrees of freedom. You want to have, if possible, several extra catchments to make your model more robust. Okay? And this indicator of performance takes that automatically into consideration. Another difference. Here, we were able to plot on a two-dimensional plot the predictor and the predictant, the predicted variable, right? Because we just had one predictor. But in case we have P predictors, this representation is no longer usable, no longer viable. So normally, a multi-regressive model you represent in this way. Here you put the empirical values, and here your regional estimates. What do I mean? These labels will be used in all the diagrams produced by the R script I gave you. Empirical values are the mean annual flow values we got from the observation, the average of all daily stream flow available for a given catchment. Okay? If you think it's not a theoretical value, because we only have a few years based on which we compute the mean annual flow. This is why I called it empirical values, because these two are estimates of the mean annual flow. If we had infinite years of observation, it would be the theoretical values. Since we have 10 years of observation, it's still an estimate, okay? And I called it empirical values. What is this value instead? This is the value coming out from your model. Okay? The line here is not the model any longer. The black line here, which was the model here, A plus B times the log of area, is this straight line here. It's the model. Here, instead, the black line is not the model at all. It's the bisecting line. It's the geometrical property of the quadrant. It's just a line indicating when regional estimates, or estimates coming from the multi-regression model, are equal to the empirical values. So you want your circles to be close to that line. The closer the circles are to the line, the better the model, like before. But while before the black line was the model itself, here it's not the model anymore. Okay? It's just a comparison between what you want to predict and the prediction you actually get. Is this sufficiently clear? We're good? Now we have a problem. I'll go back to what I was starting to say before. We have a problem. Why? Because aside from the tools we will use in R to set up the model, because then we have many possible options. There are several ways to combine a number of catchment descriptors, right? So which catchment descriptors do I pick? Which one do I use? And how many of them should I include into the model? The more catchment descriptors I include into the model, the less degrees of freedom. And so the least robust the model is, the less catchment descriptors I include in the model, the more rigid the model is and imperfect, let's say, because it looks only, for example, at the size and not at the climate. So on one hand, I want to include more catchment descriptors, but on the other hand, I have to be aware that my model is less robust, so with a higher uncertainty when eventually I will apply it, less robust with a higher number of catchment descriptors relative to the number of observations I have, the degrees of freedom problem. So, which variables do I select? Which one do I pick? Now, in order to address simultaneously these two problems, there's a procedure called stepwise regression analysis, okay? Which is the procedure we will use. It would be possible to automatize this procedure, make everything be dealt with by the computer, but we would not understand anything. We would not understand the rationale and how it works. So manually, we will implement the so-called stepwise regression analysis. Why is it called like that? Because step by step, you start from the simple model, the one with only one predictor, the one that is highly correlated with the variable you want to predict. Easy guess, it will be the size of the catchment. The larger the catchment, the higher the mean annual flow. And then step by step, you see if by adding additional explanatory variables and additional predictors, you improve your model performances, taking into account the degrees of freedom, okay? So theoretically, but we will see the application soon, the first step is to decide the significant level of the statistical test we will be using to check if a predictor is significant for the model or not. If it's informative to predict the variable we want to predict, the mean annual flow. Normally, a significant level of 10% is selected. Then when we have set the significance level of the model, we start. And we start, well, no predictor in the model, we will not even consider. It would be the average regional value, but it makes no sense when in our region you have catchments of 20 square kilometers and 1,000 square kilometers. A value that fits all will not work. So we will skip this crude model that consists of the regional average of mean annual flows. We will start with one variable model, the one that uses only one predictor, the one that shows the highest correlation, and then at each step test what happens, including another variable, okay? And we stop when we see no more improvements in terms of adjusted R squared, okay? So these are the few things I wanted to say from a theoretical viewpoint. These have to be clear, though, before we start. If you have doubts, please let me know, okay? What we're going to do next is actually to build the model in R, okay? All the steps are already in the script I handed to you, but now we will clarify the meaning of each step. Is that sufficiently clear? Okay. Let me go back here then. Unfortunately, I was not able to start Teams correctly today. It doesn't work in this room. So I'm using Teams via browser, which reduces more the space. Please let me know if the fonts are not readable when I will be working on art. Alan will be there helping out. First of all, I want to recall what we have in terms of available information. Now I have to press. I think I have it also here, so let me get it from here. So this is our practical activity. We will now address task 2, second point. The regional model to be developed consists of a multi-regression model that enables one to predict the long-term annual mean flow in an engaged site as a function of relevant catchment descriptors, physiographic and climatic catchment descriptors. This is the shape of the model, the mathematical general expression we will identify, and the omega here are the x values there, okay? This is simply the structure of the model. Now, what I wanted to look before we start with you is this. The number of catchment descriptors we have. Our list is not that extensive. We could come up with more, but what I want you to understand is the general procedure to set up a multi-regression model. That's my point today, okay? So the variables we have to set up the models are this. Catchment area, help me out. The mean elevation, then there's that exposure angle theta, then there's the mean annual precipitation and the mean annual potential evapotranspiration, okay? So I have 1, 2, 3, 4, 5. 5 catchment descriptors I could use. I could set up a model with 5 descriptors or a model with 4, but which one to pick? Or a model with 1. Because if the model with just 1 descriptors performs better than the model with 5, I will go definitely for the model with 1 descriptors. More robust and smaller number of parameters to identify, it means more degrees of freedom to the problem. Better, more stable and robust statistical relationships. You understand this point? So I want to understand which one to pick. And the stepwise regression analysis consists in several steps. At each step, I will consider and look at the performances of models with increasing complexity. So the objective of the first step is to identify which catchment descriptor, if any, because we might also find out that none of these catchment descriptors are good, okay? Which of these catchment descriptors to pick in a one variable model. This is our first step. Back to the R code. So, practical activity, I need my prostatic device to continue. This is the prostatic device, I can continue. So, practical activity on flow duration curves. and then I open the general script, okay, the usual one, by double clicking on it. It will take a couple of days, as usually. Okay. Now we're ready to start. Please, today, follow me step by step. And in case you get on a stall, let us know. If you have any issue, problem, error messages, let us know. Please do not do what I'm going to do now. I just now want to show you one very important thing. Well, first of all, you're just like me. You have your script open and you're ready to start? Good. Let's make a double check. Write dir, open and close square parentheses to see if the working directory is actually correct. Is it correct? Good. Please do not do what I'm going to do next. I will tell you when to start doing what you want. All the part of this long script we use so far are general and flexible, meaning that you simply change the number of the target code and everything works automatically, producing results for a different target site. So we always work on site number 5 so far, but if I write here 2, if I recall well, this is the small little catchment Reno et Porretta, catchment number 2. If I put 2 here and I launch all the lines that we've seen so far, point 2, second point, regional model of median AFTC, multi-regression model. So this is what we're going to do today. If I select all the lines up to here, I've selected them all. I just changed it 5 into 2. I launch it. What I get is the application and corresponding diagrams for a different catchment. In this case, Reno e Prato. Okay? I just want to point this out because from now on, with the stepwise regression analysis instead, this automatism doesn't work. Meaning that the model we will end up identifying depends on the information we have. If we exclude Reno et Pratia from the set, we will identify a model that we then will be using for Reno et Pratia, because we will still work under the same hypothesis. We will pretend our target site is engaged, so we'll throw away all the observation of discharge coming from that site. Okay, so from now on, it's really a step-by-step procedure, and the result you already have in your script are associated with a data set that excludes Savio et San Carlo. So number 5. If you decide to work on a different catchment, you have to change the results accordingly. Is this clear what I said or no? So up to now, our script is automatic. You change the site, the target site, everything adapts. From now on, it's not like that anymore. So first thing I'm going to do is to switch this back to Savio et San Carlo so that we don't have issues and we all obtain the same results that are noted also in the script. I will select all the lines, launch them, and what I have now in the environment, and you should have the same, please do so, are all variables and data sets associated with target site Savio et San Carlo. Are we good to go? Good. You will see some warning messages because now I'm going to squeeze a bit the area for the plot. So unfortunately, in my console, you will see some sorry, I'm starting to become tired. some warning messages, but no problem. We have a problem instead if you do see warning messages in your laptops, okay, or error messages. In case that happens, let us know, me or Alan. Good? Ready to start? Okay. First step, what am I going to do here? You remember what MAF is? It's a vector. I'll show you. It's a vector where we saved the empirical MAF values. So we computed the mean annual flow for each and every catchment in the region. 2, 5, 6, 7. These are the codes, and these are cubic meters per second, the empirical MAF values. Meaning we have there what we want to predict with a model. Good. As you can see, the first step I take is log. So I log transform the mean annual flows because we have to linearize our problem. So I'm storing in variable y the log transformation. Is it log in base 10 or is it natural log? If I write like this, who knows? Who knows? Do you know? I don't know. Do you know? It matters. It doesn't matter. The important thing is to be consistent. So it could be natural log or base 10 log. Important thing is to be consistent. And what do you do when you have doubts on a function in a script? What do you do? Help. Yes, I agree. So, in case we want to check this, I go here, tab help, I look for log, and this is log base logarithms and exponential. You have a list of them. I can tell you that log 10 is the base 10 log, whereas log like this, it's natural base log. Is it important? No, but it's good to know. Why am I saying it's not important? Because you can linearize the problem also using a base 10 log. It's the same. Important thing is using base 10 log here and also here. Okay. Log written like that is natural log. Now, next line, y is now overwritten with a part of y, the one that differs from the target site, which names of MAF, what is names of MAF? Names of MAF is this, 2, 5, 6, 7, 2, 5, 6, 7. So consider only the elements of y that have a name, which is actually a number, that is different from 5. What am I doing? Like I did last time, I am dropping the target site, pretending it's engaged. I am no longer using the information coming from Saviot-Sankar. So I launched this line 2. First I have to launch this. Then I launch this line 2. And if I look at it, site number 5 disappeared. It's no longer there. I'm not using the information for that site. So far I have launched this line and this line. I'm doing exactly the same thing with the attributes. You remember we have a variable called attributes. We have it already in our environment. It's up here. If we want to have a look at it, it's something like this. The attributes are stored in columns 1, 2, 3. From the third column on, there are the attributes. Okay? So I have to do exactly the same thing. I have to log transform the attributes. And therefore I store in variable lowercase x the columns from 3 to 7 log transform. Line 241. Next line, I'm doing exactly the same thing. X is now all the catchments, the log transform catchment descriptors, but Savio at San Carlo is no longer there. X is a matrix. We can have a look at it. This is the matrix. You see there's A, mean, theta, map, and MAPE. These are log transform values, not natural values anymore. Remember this. And Savio at San Carlo is no longer there. Okay? So we're ready to start. We pretend that Savio at San Carlo doesn't exist, and based on the remaining 11 catchments, we want to set up a multi-regression model. And here we go. So we will use, setting up the model, only one function, LM. It's a function of base R. It stands for linear model, and it performs everything associated with linear regression. It produces the model, tests the main hypothesis, shows you the statistical coefficients identified with the minimum least square optimization method. Okay? Before we start, I'll show you how it works. I copy this and I'm pasting it right here. This is how to use this function, okay? The syntax is this. With the syntax like this, within the round parentheses, y tilde $A. $A, what is it? It's the column with name A in the matrix of log transform attributes. So these are the area values, okay? Log transform. This syntax with the tilde tells R, test a linear model between y as predicted variable and A as predictor. Test this model. If I launch only this command, what I see is what is plotted now on the console. So it tells me this is the syntax I invoked. It's a one variable model, and it tells me the coefficients, intercept and slope. Slope is more or less 1, okay? This is common for one variable model that wants to predict the mean annual flow. If we were predicting the 100-year flood, the slope would be less, 0.6, 0.7. It's natural to obtain almost a linear relationship between area and mean annual flow. But this model is not very good, and we're going to see this very soon, okay? So if I launch this line as is, the line returns just the two coefficients. Did you get what the coefficients are? The two coefficients are the intercept and the slope of a model with just one variable, okay? So it's basically the log transformation of the first multiplication coefficient and the first exponent. This formula, though, does many more things. We realize it if we launch line 251. If we do, we will see the entire output of LM in a new object in R. First of all, why did I call the object in that way? It's just a way in which I remember what is the meaning of this linear model. It is a model with just one explanatory variable, then I use the dot as a separator, and I note here that the explanatory variable I'm using, the only one explanatory variable I'm using is A. Okay? I launch again the same command and store the output in this object. So I'm doing this. If you notice, the global environment now shows an object which is a list. You remember what a list is? A list is a complex objects that group together several objects. Some of them might be text, some others might be numbers, some others might be vectors, matrices. Recall the first class we had. I can explode the list and see what's in there. We were just seeing coefficients before, but there are also the residuals of the models. There are other different things, the fitted values, the model predictions. This is what fitted value mean. So there are many, many other elements in this list. They are all interesting, but we have a limited amount of time, so we will stick to our plan. I will show you how this function can be used in a stepwise regression framework for identifying a regression model. Now, if you launch summary of the object, it provides you a brief representation of that list. Let's look at it. I launch summary, and this is the output. You should not have warnings. I do, but you should not. So it summarizes the instruction I sent to the console. It gives me an indication of the distribution of residuals. So the median residual is 0.1 in the log transform space, and the residual vary between a minimum and a maximum. 1Q, 3Q is the first quartile and third quartile, so the 25th percent, 75th percent. I have a, let's say, box plot representation of the residual, if we recall the box plot. Now, this is the interesting part, the one I want us to focus on. Coefficients. Here we find, again, the two coefficients, the intercept and the slope. Okay? And then there are statistics of these two coefficients. In particular, a test variable, the variable used for a statistical testing, and a probability associated with this test variable. Remember when I said, let's set the significant level of our statistical testing? This is the part. What is the statistical test testing? It's testing this. What is the possibility that, based on information I have, so 11 values of log transform mean annual flow, 11 values of log transform area. What is the probability that with least square regression I get this as the value of the intercept, but in reality the intercept is 0. There's no intercept. The value is 0. I obtain that only because the 11 values I have are those. Okay? And the probability you can read right here. The probability with those 11 observations of mean annual flow and area that the intercept of the model is 0 is 0.007. So a very, very low probability. It means that the intercept of the model is statistically different from 0. Maybe it's not minus 4.3, maybe in theory it's minus 4.5, but based on the 11 values we have, minus 4.3 is the value we get. But what we know with a very, very high at this point probability is that there has to be an intercept. The intercept is not 0. And this is also graphically highlighted with these flags. 2 stars mean a very low probability, so highly significant. 3, even lower probability, a probability close to 0 that the intercept is 0. The problem arises when you see a dot. Dot, it's our entry significance level, 10%, no, from the slides. I'm referring to the slides. We use the 10% as the threshold to accept the possibility that the intercept is different from 0. You will see no flag, 0 flag, if this probability, I say it again, the probability that the theoretical intercept is 0 when we actually get minus 4.3. If this probability is high, it means that the value we have here, it's of 0 value, 0 importance, because the intercept might as well be 0. We get this value only because of the way in which points are aligned in that diagram. Is this sufficiently clear? Is it clear or not? So when we see no flags, it means that the intercept might as well be 0 with a high probability. Even more important, the second coefficient, because this tells us the probability that the slope of this model is 0 based on that 11 pairs of observation. If the slope is 0, it means that what we want to predict that does not depend on the predictor. It means that that variable is not relevant. You can drop that variable because it tells you nothing, okay? But look, we obtain a slope of 1, and the probability that theoretical slope, which we don't know, is actually, based on those 11 pairs, is actually 0, is again 0.1%. It's a very low probability. So, to conclude, the outcome of the summary tells me that the intercept has to be different from 0, and it tells me that area is a highly relevant and informative descriptor if we want to predict the mean annual flow, which is something we would expect. Okay? Below, adjusted R-squared. We're not interested a lot in the R-squared because we will compare models with 2 descriptors with model with 1 descriptor. So we want to take degrees of freedom into consideration. Adjusted R-squared, 0.65. I think we can do better than that. It's not close to 1. It's already, let's say, a good value for just 1 descriptor, but it's not very encouraging. Perhaps we can do better adding more variables. And perhaps we can do better using another of these catchment descriptors. So let's note this down for the moment. First step, the adjusted R-squared there is 0.65. I'm rounding to the second digit. Okay? P-value, this is the p-value of the model. This too has to be low. It also takes into account the degrees of freedom. So these are the 2 numbers we will be looking at in comparing different models. This has to be high, possibly close to 1, and this has to be as low as possible. Okay? These are the 2 numbers we will consider. Now, the following lines tells you how to extract elements from a list. You can do it in 2 ways. This is the first element of the list. The first element of the list is coefficients. The first object of the list. And writing this, you are extracting from the list the first element of the first object. So if I launch this, I get the intercept out of that variable. Exactly the same result I obtain if I write the name of the object, then $, then coefficients, and then 1. Exactly same output. This is just in order to tell you how to get value out from that list, so that, for example, we can use the intercept and the slope. Okay? Now, stepwise regression analysis. I have to check all one-variable models and see if there's any model that performs better than this one. Very easy to do. I run again the same command. I just change the name of the object where I store the result of the model. Same logic, same rationale. Model with one explanatory variable, only the mean elevation relative to catchment outlet. Okay? So I launch this line, I get the summary. Looking at the output, what can you tell me? What can you tell me from this output?
Better not to consider it.
Why?
Because the adjusted R-square is very low.
First of all, if you are a pragmatic person, you immediately go and check out the R-square. 0.009. So not even comparable with this. But if you want to look at, let's say, statistical significance of your model, what do you see? You see that we got an intercept value. Actually, it's high. No, it's higher in absolute terms than -4. It's -8. It's even higher than before, right? But we got this number here. But it could have happened just by chance. The probability that the theoretical value of the intercept was 0, it's actually not a negligible one. I have 40% probability that I see -9, but it's actually 0. Okay? Mean elevation used on its own. I got a slope, a high slope. It's a non-linear model with an exponent that is higher than 1. So mean annual flow increases more rapidly than the mean elevation. Actually, yes, increases. But the probability that this slope is instead 0, which would mean the opposite. Mean elevation is irrelevant. Mean annual flow does not depend on mean elevation. The probability that this is 0 here is 32%. So definitely higher than 0.1, which we set as the threshold, which is set as the there's no legend because there's no flag here. Okay? So, even without the R-squared, which I'm not even noting down, looking just at the statistical relevance and significance of the model, this is not a good model. Okay? I'm not even going to consider such a model. Okay? Clear? And then the rest goes automatically. I have here a model that considers only theta. How does it work? Good or bad? Very bad. Here too. Probabilities for the intercept and the slope of being 0 are actually above 10%, both of them. Another very poor model. What about mean annual precipitation? It's easily checked. I launch this, and I get this output. Again, this is rather surprising, but this is what the data tell us, okay? Mean annual precipitation I stress this again, on its own, it's not enough. It doesn't tell us anything. Mean annual potential evapotranspiration. Well, if the rainfall doesn't do it on its own, I expect that the potential evapotranspiration, which is just temperature, won't either. I launch and check the outcome, and the outcome is this. So in reality, we check 5 different one variable model, but there's just one model that is statistically significant, and it's the one with catchment area. This is the only one, okay? So catchment area makes it to the second step. What is the second step? It's probably very easy to understand it now. The second step is to check all possible models with 2 explanatory variables. One is the area, and the other one we have to understand. Okay? So, catchment area makes it to the second step. Let's see which, between these 4, is the explanatory variable that makes more sense to include into the model. So, is this difficult to implement? No, we do exactly the same thing. We slightly change the syntax. Now we are considering linear regression models with 2 explanatory variables. One of them will always be the log transformation of catchment area. Okay? So this is done exactly with the same mathematical expression. I launch this, I get the summary with area and theta. What do you see from this table? What do you see? Is it a model worth considering? What do you think? Tell me. Talk out loud so that I understand if the message was delivered. What do you see? Is it a model you would like to consider? I'm becoming very sad.
Yeah. Just in R squared.
It's good. Yeah. So let's go for it. Or not?
No, we have to try the other ones also.
Why? No, but are we considering it? Are we considering this model?
Based on the adjusted R square.
Based on adjusted R square, but I spent a lot of time on the initial part of the output. And what does the initial part of the output tell us?
If I use it, I have different.
Speak out loud, I cannot hear you.
If I lose it, I have different outputs.
If you look at the statistical test that tells if or not, whether or not an explanatory variable is significant, what do you see? You see that the intercept is highly probable that it's different from 0. The slope associated with area, it's highly probable that it's different from 0, or the probability that this 1.3, interesting, it was 1 on its own, but now we mix 2 predictors and we move from 1 to 1.3. It happens always like this. I'll spend a few more words on this. But this is 1.3 coming out from the least square regression method, and it's highly probable that it's different from 0. And what about this? We obtain a slope that is different from 0. But the probability that this happened by chance, entirely by chance, based on the 11 observations we have, is high. It's close to our threshold, which was 10%. When I say 10%, I don't know if I got this point sufficiently clear. I'm referring to this slide. We set the designer of the model, the engineer sets 10% as the significance level, okay? So then we have to be, let's say, fair. We set 10% as the significant level. We obtain 10.6%. That's above the threshold, right? So
The 10% is
it could be significant,
the 10% is the limit.
but not enough to us, because we decided that we want to have a model that is statistically significant at 10% level. Okay? So this line here tells us that this is not enough. So although we obtain a slight improvement in terms of adjusted R-squared, the model is not robust enough. I'm not even considering this model. Okay? Is it sufficiently clear? I'm not noting down the adjusted R-squared value, which is slightly higher than 0.65, because this statistical relationship is not significant enough, robust enough.
Sorry, but this is theta, right? Not mean.
Ah, sorry about that. You should have told me before. Thanks a lot. I was following this order, but apparently you didn't follow that order. Okay?
Yeah.
Thanks a lot. I did it on purpose. I wanted you to understand.
Yeah, we just jumped 1, 2 lines of the code.
Ah, we jumped that. We can go back. Let's go back. Theta is here. And mean elevation is here. So 1 and 2. Now, what do you tell me?
Adjusted paragraph is okay.
Now, for the very first time, we see 3 stars. The probability that these 3 numbers are 0 is extremely low, super low. And in fact, we got the maximum in terms of flags. So this is a very significant model. Both descriptors are informative. Together, they help in a better prediction of mean annual flow. Do you want to have this confirmed even in a stronger way? 0.93, which is already a very, very good value. Orange. I now have to find orange again. So, a model with 2 variables, A and mean elevation, gets us all the way up to 93. Theta we checked. It didn't work very well as a model.
In this case, you are not considering the threshold of 10%.
If you were, let's say, less strict, a significance level of 15%, it would have been a model to consider. But do you remember the adjusted R-square was around 0.7, 0.93. This is hard to beat. Okay. Thanks for the comment. So theta we did. Precipitation. So here we combine the size with the amount of rainfall. 1 and 2. Again, 3 stars. Okay? Again, a very high value. 0.96. And an overall p-value of the model that tells you how robust the overall model is, which is again extremely low. So this is another good model. If I were to choose between the two, I would go for catchment area and mean annual precipitation. Now, we still have a couple to test, I think. No, one to test. Potential evapotranspiration. Summary. And this is our output. Again, 3 stars. So these two descriptors are both significant. And again, a rather high value of the adjusted R squared. But not as high as... Did I round up well? It's 0.94? Okay. Conclusion of the second step. Do we stop here? We identify the best model. Which model do we consider? Which model do we consider?
96.
We have to go to the third.
No, I want you to tell me the conclusion of the second step before we address the third one.
Area combination between and no precipitation.
Very good. So area makes it to the third step, and mean annual precipitation makes it to the third step. These two variables are to consider. Okay. Now we have to test the 3 remaining models. Yes, the 3 remaining models, 1, 2, and 3. They will have area and mean annual precipitation always included, and then they will rotate these variables. Let's see how it goes. Let's see how it goes. So, again, same rationale, see? Model with 3 explanatory variables, and the variables are area, mean annual precipitation, mean elevation. Let's see how it works. I send it and I ask for the summary. What do you think? What do you think? Tell me, please. There's no error at this phase. It's not an examination. Tell me what you're thinking based on the outcome you see on the screen.
Just R seems to the same value as before.
We are around 0.96 again. To an engineer, 0.957, 0.955, we're talking about really decimal of a percentage if we consider adjusted R squared a percentage, right? Not very different. But we lose a degree of freedom. The model is less robust. The model is more complex. It has 3 explanatory variables instead of 2. I would have no doubts on which model to prefer. Also because the last variable we added is not very informative. The slope is 0.7, but it might as well be 0, and the probability that it could be 0 based on those data is 40%. Do not forget to have a look at this column. It's very important. Don't just focus on this. Okay? So this is a model that I would not actually even consider, because the statistical testing tells me that this additional variable is not that informative. Okay? Let's see the next one in line. Next one in line is, now you understand, I think, the rationale. Area, mean annual precipitation, theta. What do you say? Same. Same, exactly the same. Next model is area, mean annual precipitation, mean annual potential evapotranspiration. What do you say? Adding mean annual potential evapotranspiration even confused the situation, because now we don't have stars, not even in the intercept, and the mean annual precipitation. We still have adjusted R-square around 0.95, but because area and mean annual precipitation are still within the model, okay? Plus, now, intercept is not statistically significant. The slope of mean annual potential evapotranspiration is not statistically significant. We reached a conclusion. Okay? Our model is a model with just two predictors. The mean annual flow, based on those 11 catchments, I will predict using the size of the catchment times the mean annual precipitation. And that's it. 3 parameters to estimate and a very robust model. Plus, actually, a good and inviting model with an adjusted R-square very close to 1, actually. It's not easy to find. In real-world situation like this, it means that the data we have at hand are accurate and clean.
Can we just,
yes.
Doing the third step, we just eliminate theta as well, you know, because after 2 steps, we consider it as a factor to consider.
Yeah, yes, in reality, the stepwise regression procedure would imply also different testing. At each step, you start removing back one of the variables and check if the situation. I wanted to keep it simple, just to pass the rationale. In a situation like this, with just a few catchments, 11 in total, okay, just a few catchments, it doesn't make any sense to go further. Testing the 4th step, when already at the 3rd step we obtain this output, it's not very sensible, because it would mean that I lose yet again, another degree of freedom. So my model would be less and less robust. Did I answer to your question? Okay. Everything is clear for everybody? Okay, now the rest is just about, the rest of the script is just about representing the results and checking the overall regional model prediction accuracy. I will go through the lines. You have the original script with you, with the line numbering that is still the original one, or you added some lines? You didn't add any line, not even this one here. At the very beginning, I added a line here. You did that too?
No.
Ah, good. Good for you. So if you have the original script, I can go through it with you. So next lines that on the original script are lines 320, 321.
Yes.
These two save in different objects what? The mean annual flow for all sites but the target one. This is this empirical mu q, which I could have named empirical MAF. This is what it is, the empirical MAF. I'm storing it in an object for producing a plot, and also I am storing the empirical value of the mean annual flow for the target site. Do you notice the difference? Here you have exclamation mark equal, which is different from. Here you have double equal, which is equal to. These are two logical operators. So here I'm saving just the other catchments. Here I'm saving the target catchment. The regional μ_q, what is this? These are the estimated values. How do I obtain it? From the model which we proved to be the best performing one. So two variables, area and mean annual precipitation. There's an object inside that list that is termed fitted value. But if I use fitted value, I obtain these numbers. 0.4, here 1.7, here a negative value altogether, a negative discharge. Keep in mind that these are the fitted values after the log transformation. If we want to have discharges, cubic meters per second, we have to back transform the fitted value into value in natural space. Okay? Do you understand what I'm talking about? So, these values here, I take the exponential of, so that I back transform them from logarithms of discharges to discharges. If I send this line to the console, this is the output. And these are all positive values, and these are our estimates. These are the prediction using this model. Okay? Please upload that to the shared drive so that also the two students that are not here. Would you do that? You took a picture of the blackboard? I would be very happy if you could upload it to the shared drive.
Okay, yeah, absolutely.
Thanks. If you have doubts about doing that, let me know. So I'm storing also this just to represent them. And then I'm producing a scatter plot. Line 332 here, one line less probably here, it's just options to beautify the diagram. So it adjusted the margins to have more space and write the title of the plot and the labels of the axis without overlaps. Then the plot itself, the first plot I'm opening, reports empirical values of mean annual flow on the x-axis and our fitted value on the y-axis. It's a log-log diagram, so the scales are in logarithms, and the rest of the arguments are just, again, to beautify the plot itself. So this is the diagram we produce. Each and every circle is the comparison between the empirical value of the mean annual flow and our prediction, okay? These circles do not include the target site because we dropped that. This is the information based on which we develop our model. AB line, it's a way to plot a line on a diagram given the intercept and the slope. So this line plots this command. I have to look at the time, sorry, I don't want to go extra time. This command here adds a line to a plot, provided that you indicate the intercept is 0, and the slope is 1. This is the bisecting line, okay? It's the line of perfect fit, which we use as a reference. The fact that the black circles are close to this line means that the model is actually nice. Then, this is an addition from Alan. If you're curious, you have the codes of the site added to this plot so that we know that For example, this is site 32, this is site 7, site 9, site 28. These are all the sites we use. Do you see site number 5? No, because we dropped it. Okay? The predictions are not at the same level of accuracy for all the sites. Some sites have smaller residuals, some sites have larger residuals, right? It's very good, though, that we got the high value and the very low value more or less with similar accuracy. Now we add to this plot, a point, a single point, which is our target site. How do we do that? First of all, we have to apply the model we developed. This is why I told you that this is not automatic. This model we developed by dropping Savio at San Carlo. If you drop another site, maybe you get a different result. Maybe including the mean elevation for those 11 catchments improves even further. But for Savio at San Carlo, this is the outcome we got. This is why I'm saying it's not automatic. So if I want to compute the target mean annual flow, I take the exponential of what? The intercept plus the log transform area times the coefficient for the area, which is coefficient number 2. Then the log transform mean annual precipitation times the coefficient number 3, which is the one for the mean annual precipitation. This is our prediction of the mean annual flow for Savio at San Carlo, 6.6, almost 7 cubic meters per second. And this, instead, is the empirical value, 7.7. Okay? They are not the same, but keep in mind that this prediction we obtain without using any information on the observed discharge. Using a regional model, and when your regional model performs this way, let me tell you, it's a great regional model. Of course, you will have some residual, some uncertainty between prediction and empirical value, but if this is the difference between the two, you're doing great. Okay? Now, let's add our point to the diagram and let's add some text. So this is red to remind us that this information was not there when we developed the model. Okay? And this is actually how our model performs for site number 5. Normally, when you develop a model like this, you apply a leave one out cross-validation procedure. So in order to see if a model with area and mean annual precipitation works fine in your region, you drop site number 5 and see how it works for site number 5, as we did. Then you put number 5 back in and you drop number 2. You drop number 2 and you see the model you developed without number 2, how it works for number 2, okay? You do this iteration for each and every site to have an overall idea on the performance of your model for your entire region, not just one catchment as we did. Okay? This is called cross-validation procedure. Actually, leave one out because at each and every iteration you leave only one site out. Do you have questions on this? No? Now we are wrapping up our practical application. What I'm going to plot here is a comparison between predicted flow duration curve and empirical flow duration curve, combining the two elements of the model. combining the dimensionless curve, we identified, I wanted to skip right to that slide, but it was impossible, combining what we did on Monday with what we did today. Okay? If you see, I am basing plotting against the duration, the empirical value of mean annual flow times the regional prediction times the empirical dimensionless flow duration curve. And I open a new plot. These are things that we saw already, so I'm going a bit fast. Tell me if I'm going too fast, though. What is this? This black line here is the empirical median annual flow duration curve for Savio at San Carlo. On top of it, once I add the tick of the axis, on top of it with lines, I'm now adding in red our prediction. So our estimate of the mean annual flow, 6.6 cubic meters per second, times the dimensionless flow duration curve we obtained with the region of influence approach. Here is the target regional prediction of the mean annual flow, and here is our region of influence prediction of the curve. The output is something like this. Empirical value, our prediction. Okay? Again, the agreement between the two is rather good. This is a very good outcome for a regional model. There are some discrepancies in the intermediate part and in the low flow portion of the curve, which is always the hardest one to predict. If we want to quantify this, we can plot the relative residual. So as a function of the duration, basically, the empirical value minus the prediction divided by the empirical value, just to have a representation of the error. If I launch these lines, this is our outcome. It tells me in relative terms the residuals as a function of the duration. This is 50% error, this. This scale is natural, so it means that our prediction is within the 50% error, which is very good for engaged catchment, up to here. We cover this range of duration very, very well. We have a prediction error of less than 50%. I stress this again, without using any discharge information from the target site. Okay? This is a very good outcome. Of course, the last bit is the most difficult to predict. And here it's where, of course, we get the highest relative error. Also, they're very high because we are dividing by very small numbers. The empirical low flows are 0 point something, so in relative terms, errors increase a lot. Okay, in absolute terms, differences are a few decimal of cubic meters per second. Easy? Clear? Okay. Just for you, as a gift, a few lines as an example below that show you how to save all the information we produced in a new Excel file. So saving data from R to Excel file. This function cbind It's a column binder. We will bind together in different columns on a single data set several information. The empirical median annual flow duration curve, the duration, and then the dimensionless curve and our regional prediction. Round is a way to round numbers. We don't want to write in the Excel file a lot of decimals. We don't need them, so we will just keep 4 decimals. So if I launch all these lines, all of them, it will save this information on a site, an Excel file, whose name also include the number of the code automatically, site _5 _AFDC50. This name is created automatically if you look at the lines. And the content of the Excel file is something like this. You have the 3 curves that then you can plot or use quantitatively in your assessment. Okay? Duration, this is the empirical curve for our target site, the predicted dimensionless curve, and the predicted dimensional curve. Of course, 50% uncertainty is still a lot. But these models you use when you have to make a first rough assessment on the water resource potential. Of course, between deciding to have a plant in a given location and actually building the dam and the diversion canal, designing it and building it, it takes several years. What do you do in these several years? You start right away with a monitoring campaign. You set up a stream gauge where you want to build your facility, your plant, to have some observed information to refine your regional model outputs. This is very important, okay? Since years will pass between starting to think about designing a power plant and actually constructing it and having it to become operational, several years. If you have 3 to 5 years of data available, it has been shown that this information is already enough to have much better prediction of your stream flow regime. Okay? This is an important point. Okay, I'll go back to our, and then I'll set you free, I promise. I'll go back to our practical activity on the prediction of stream flow regime through flow duration curves to see the task we have. Constructing and plotting empirical flow duration curve, we did it for a given site, and then producing a regional prediction for the same site, pretending the site is engaged. Task 3, it's the last bit we saw. Test the reliability of the model through that error duration curve, for example. Task 4, in group work, it's suggested, try different target sites or try different flow duration curves. We work on the median annual flow duration curve, but the same exercise could be developed, the prediction could be developed for the period of record. This is optional, let's say, for the assessment. You will bring with you, you will submit a report addressing these tasks. These tasks can be addressed for Savio San Carlo median annual flow duration curve, and I'm perfectly fine with it. Or you could decide to show the result for a different site, okay? To show the result for a different definition of the flow duration curve. For example, the one for a very dry year, which is super hard to predict, and you will see if you do. Okay? It's a suggested group work if you want to meet and work by group. But I repeat it, to me, it's perfectly fine if we discuss a report that focuses on Savia San Vittore. Next class, I'll show you an example of a report to finalize this activity. Okay, I'll provide you with an example showing you how the report is structured. Okay? Do you have doubts on what we've seen today? Everything seems to be clear. The syntax of the last command, I did not have time to go into the details, but in case you have a problem with that, please ask me, ask Alan, ask ChatGPT, and you will solve your problems. Good. Ciao. See you next week.